In chapter number 5 of linear integrated circuits, we are going to discuss linear operational amplifier circuits. In particular, we will discuss three different types of circuits. We will discuss integrator circuits, where the output will be proportional to the integration of the input or area of curve, area of the area under the curve of the input signal. We will discuss differentiator circuits, where the output will be proportional to the differential or derivative of the input, and then we will discuss a set of phase shift circuit, where the output phase is going to be different than the input phase, but the magnitude is going to be the same. So in the first video, we will start with the integrator circuits, and then there are two integrator circuits: true integrator circuit and AC integrator circuit. So we're gonna look at both of them in this video. True integrator circuit is basically the same idea that I explained, that any input that you have, the output is going to be integral of the input times a constant value, which is the gain of the integrator. So if your input, let's say, is a square wave, the output is going to be whatever the gain of the circuit is. Let's say gain of the circuit is A, times integral of this, that is area under the curve. And remember, when you take the integral of a square wave, let's say you're taking the integral of a constant, so you have a constant value, let's say you have a constant value k and negative k, it goes between negative k and k. So constant of any integral of a constant value is a slope or function of t, right? Likewise, integral of a negative constant value is a negative slope or negative function of t. So you can expect the output to be a times t or negative a times t, or in other words, it is going to be like this. So remember, if you have a square wave, the output is going to be a triangular wave. If you have a triangular wave at the input, again you're going to calculate area under the curve. Let's say this is the 0 axis, so you're going to calculate area under the curve, as we will discuss shortly, and the output is going to be what? So your input is now this, so output is going to be a function of t square, right? So output is going to be a parabolic like output, a quadratic like output, like this. It's not sinusoidal wave, but a square waveform, the quadratic or parabolic waveform. If you have a sinusoidal input, integral of sinusoid is still a sinusoid, so you're gonna have another sinusoid at the output. So this is a basic idea. Again, the idea is whatever input you have, the output is going to be the integral of that output times gain of the circuit. So let's look at this basic true integrator circuit and look at the derivation. Derivation is the same that we have discussed, that at your virtual ground, the current that is coming here will be equal to current that is going in the feedback loop. So your V input over R, which is here, current, will be equal to the current through the capacitor, and the capacitor current we know is IC is C dV over dt, where dV is the voltage across capacitor, and the voltage across capacitor in this case is 0 minus V out. So VI over R will be equal to negative C dV naught over dt, or C derivative of 0 minus V out over dt. That means the output, you take the integral of both sides, and the output is going to be negative 1 over RC, which is the gain of the circuit, integral circuit, and the integral of the input, plus of course you're taking the integration from 0 to t, then you're gonna add the output value at 0. So that's going to be the output of the circuit. It is the integral of the input times a gain. And remember, this negative sign means that when output has positive value, the slope of the when input has positive value, the slope of the output is going to be negative, and if input has a negative value, the slope of the output is going to be positive. That's what this negative sign is going to do. If you have a relaxed circuit, that is the output is 0 at time t is equal to 0, then output will simply be negative 1 over RC integral of V input t dt from 0 to t. Alright, so this is all good. There is one small problem here, and actually that problem you can see when you even simulate this circuit through integrator. And the problem is because of the biasing of the circuit, 15 volt and negative 15 volt, there may be a small biasing voltage that appear at the input, and any biasing voltage which is DC that appears at the input, what's going to happen to the output? This thing is going to happen at the output. So let's say input is in nanovolt, biasing voltage that appears at the input, let's say it's nanovolt or millivolt, micro, whatever. What's going to happen that voltage over time is going to start accumulating at the output, and output will start rising with a specific slope towards the maximum value, which is in this case let's say 15 volt if you're taking 15 volt biasing, or whatever the saturation voltage is. So it's going to hit 15 volt and then it's going to become constant because it cannot exceed 15 volt or whatever saturation voltage is. So this phenomenon you can even observe in the simulation. If you simulate this circuit, then you are expecting that let me give a square wave, and you are expecting that your output is going to be this, which will be about x-axis, but in fact you will see that this voltage is going to appear at 15 volt. So this is 15 volt, let's say, and the voltage is going to be something like this over here, something like this. So that's the problem with the true integrator, that any small input bias DC voltage can make the output go towards saturation, and that's a very practical case. So what we do is we make an AC integrator. And what is AC integrator? We'll discuss shortly. I'm going to discuss differentiator in the next one. And this is something I discuss. Integrator output, if you have a constant DC, the output will be a ramp, A times T. A square wave is going to give you a triangular waveform. A square wave is and constant DC is the same thing. Of course, square wave is positive and negative DC. That's going to give you a triangular waveform with AT or negative AT. And constant DC, of course, is going to give you only one of them. If you have a triangular waveform, the output is going to be a parabolic waveform, AT square, and then your sinusoidal waveform is still going to give you a sinusoidal waveform. Alright, let's look at this example. We have a true integrated circuit with resistance 1 kilo ohm, capacitor 1 microfarad, and input is a square wave. Determine the output of the circuit. So the output of the circuit is negative 1 over RC integral of 0 to t V output t dt, and at steady state, of course, it is going to be moving between two values. And assume that output at input at 0, this is input, sorry, output at 0 is 0, so we're not going to put V not 0, we will assume it is 0. So at steady state you have this, let me see, you have right here. So at steady state, this is your input, a square wave. It is going between 0 and, let's say, okay, it's not given, let me try to read it. I think it is, let me expand this, it's hard for me to see. Okay, it's 5 volt. So it's going from 0 to 5 volt, and your time period of the input is 1 millisecond. So half a signal is 0.5 millisecond. So area under curve. Now area under curve with the same sign, that is positive area right here or negative area right here. You can calculate any of the area. And this is an easy way to do it, because again, remember, integration is calculation of area under curve. So when you calculate area under curve with the positive sign, that is above the x-axis, or negative sign below the x-axis, the area is the same. In this case, it's the area of this triangle, not triangle, sorry, a rectangle, which is 5 volt times 0.5 millisecond, which is 2.5 milli, right? Okay, so 2.5 milli is the area. Now this area times, let me go and make it smaller again, this area times 1 over RC. That is going to be the peak to peak value of the output waveform. And what will be the shape of the output waveform? Of course, input is a square, the output shape is going to be triangular waveform. So you calculate that 2.5 milli times 1 over RC. Now let's say RC, R is 1 kilo ohm, C is 1 microfarad, 1 over RC is going to be 1 over 1 milli, 1000. So 1000 times 2.5 milli is going to be 2.5 volt. So this 2.5 volt is going to be the output peak to peak value. And then the negative sign tells you then when you have the positive value of the input, the output slope is going to be negative. So it's going to start negative slope for the first half of the cycle. From 0 to 0.5 milli, the slope of this line is going to be negative because of this negative sign right here. And the peak to peak value is going to be 2.5 volts. So it's going to go from 1.25 to negative 1.25, total 2.5 volt. And when the area is negative over here, then that negative is going to be multiplied by this negative, and you have the positive slope. So it's going to go from negative 1.25 to 1.25 in the next half of the cycle. And of course this will keep on repeating. Again, this will happen after you achieve a steady state, because initially the capacitor is going to take some time to charge and discharge until it will hit a steady state. Now again, if you simulate this thing in PSpice, you will see that you will get this waveform, but you're going to get this waveform not at 0. So this the center line will not be 0. It's not going to be axis. You're going to get this waveform. This will be 15 volt right here, and then it's going to go from 15 volt minus 1.25 minus 2.5, which is going to be 13.5 volt, to 15 volt to 13.5 volt to 15 volt, and so on and so forth. And that's a problem with the true integrator. But in any case, ideally, theoretically, it should be about x-axis, and this should be the output of this circuit. So the problem that we have over there can be remedied using AC integrator. So true integrator, as we discussed, it can produce a ramp that will saturate for any small biasing input voltage, DC. So we will make a little bit of modification. Before we do that, let's observe what will be the transfer function of the true integrator circuit. So this is our true integrator circuit. We analyze the circuit in the phasor domain, in complex frequency domain. So VI, V out, and then reactance of the capacitor 1 over j omega c. So again, we do the same analysis. KCL here, current here is equal to current here, and then V input over R is equal to negative V output over XC, right? V input over R equals negative V output over XC. So H of j omega, which is V output over V input, V output over V input, will simply be negative V output V in, so negative XC over R. And negative XC over R is what? Negative 1 over j omega c over R, which will be written as negative 1 over j omega RC, which is right here. Right, so this is the phasor response transfer function of the true integrator circuit. Okay, and the magnitude of this, of course, is 1 over omega RC. Magnitude of this complex number will be 1 over omega RC, and what will be the phase? I don't think I put phase over here, but anyone can tell me the phase. Think about it. This J is going to go in the numerator. It can become positive, so you can also write this thing as J over omega RC. So what will be the phase of this? The phase of J omega is 90 degrees, right? J correspond to 90 degrees. So for all the frequencies, the phase is 90 degrees. All right. So magnitude is 1 over omega RC for this complex number, and the phase is 90 degrees. Now AC integrator circuit, the only modification we make is we add a feedback resistor in parallel to the capacitor. A feedback resistor in parallel to the capacitor. But this can create a really good circuit that can be treated differently at DC, and it can be treated differently at AC with higher frequencies. Okay, let's see how. So we go ahead and we combine these two impedances, reactance and resistance, in parallel, and we have the feedback impedance RF in parallel with XC 1 over J omega C, and we're gonna get RF over 1 plus J omega RFC. And then we're gonna write down the transfer function again. So again, the transfer function is negative ZF over R input, and then you simplify this, we're gonna get RF over R input 1 plus J omega over RB. That's going to be, there's a little mistake here. This is negative. I need to fix this. This is the negative sign here, which I forgot to put it here. That's negative sign. So make sure you fix it. I'll fix it in the notes as well. So that's negative RF over R input over 1 plus J omega RFC. So we take RFC as the time constant of the feedback circuit. We call it time constant of the feedback circuit, tau F. And then we take 1 over tau F as omega B, which is the break frequency, cutoff frequency, 3 decibel frequency, whatever you want to call it. So now observe how this circuit is going to be working. At DC, if you have a DC signal, then of course omega is 0 for DC. Or let's say if your input frequency is quite smaller than break frequency, then this factor is going to be quite small and we can ignore it. Especially at DC, this factor is going to be 0 and your gain will simply be negative RF over R input. What does that mean? Any DC offset that is in your circuit, or any DC bias in voltage that appears at the input, for that DC voltage, the output is going to be the inverting gain output. That is negative RF over R input times the input DC. Or if you have any small frequency which is quite smaller than omega B, it will approximately be negative RF over R input. But especially for DC, it's going to be negative RF over R input. And then anytime your frequency go beyond omega B, that is beyond cutoff frequency, higher than cutoff frequency, then we can ignore 1, and what will be your frequency? Omega greater than omega B, or F greater or equal to FP. So let's look at, okay, I'll just do it here. So what's going to be your H of J omega? Negative RF over R input divided by, so it's going to be approximately equal to J omega over omega B, or JF over FP. Remember, omega is 2 pi F, omega B will be 2 pi FP. So J omega over omega B or JF over FP is going to be the same thing. And that's going to give you negative, and remember omega B, so I'm going to go back to this right here. Omega B is 1 over RFC. So I can write this down as negative RF over R input divided by J omega RFC, right? And then this is going to be simply negative 1 over J omega R input C. What is this? This is the transfer function of a true integrator right here, right? So when your frequency is going to become quite larger than omega b, the circuit will start working as a true integrator circuit. So that circuit is working in two ways. For if your let's say your input has a DC component and AC component, and the frequency of the AC component is quite larger than omega b, then you can figure out the output, which will also be combination of two signals, a DC component and an AC component. Now the DC component is going to be figured out using the inverting amplifier. The gain will be negative RF over R input times the input DC voltage, and the AC component will be figured out using what we did in example, this example right here. The AC component will be figured out using this, because your circuit will be working as a true integrator at frequencies higher than omega b. So let's move on and see. This is what we are discussing over here. Let's see, AC integrator, this. Okay. So your output voltage is going to be V out dash T. Basically, V out dash T is what? The output of the AC component. Output of the AC component plus output of the DC component. So that's going to be sum of both, and you can calculate both of them separately. So V out dash T is going to be 1 over R input C negative V input dash T. V input dash T is the AC component of the input. Remember to remove the DC from that. So for example, if your input is, let's say this, and it is offset by 5 volt and it is going to 7 volt and let's say 3 volt, right? So 5 volt is the average value of that. This is the DC component. So for 5 volt, you are going to take RF over R input. Let's say RF over R input is 2. So it's going to be 2 times 5 volts. The output voltage is going to be centered at negative 10 because of this negative, right? Negative 10. The output voltage is going to be centered at negative 10. And then this voltage, first of all, you're going to put this on the x-axis because you're removing the DC voltage from the input. So the triangular wave is going to be about the x-axis. It is going to go from total peak to peak is 4, so it's going to go from 2 to negative 2. And then you're going to calculate the area under curve, total positive area under curve or negative area under curve, right? Whichever way you want to do it. And total positive area under curve is going to be the peak to peak value of the output waveform. Peak to peak value of the output waveform. So it is going to be if it is going up, the output will be going down, and so on and so forth. And the output is going to be what? The output is going to be a T square signal. Because it's a T signal, the output is going to be a T square or parabolic signal. So output is going to look like something like this. Let's say it's not sinusoidal, it's a parabolic output, right? The peak to peak value is going to be whatever the area under curve times RC, right? Area under curve times RC, that's going to be the peak to peak value, and it's going to be centered around negative 10 volt. That's going to be the output, and this is an easy way to calculate the output. So this is how it is going to be. And there is an example. Observe, this is a square wave that is given at the input, and this square wave is centered at 3 volt. 3 volt because it is going peak value 4 and the bottom value is 2 volts. So the DC offset is 3 volt. So we take the DC offset first, 3 volt multiplied by the gain of the amplifier, which is negative RF over R input, and given whatever values are given, according to that the gain is negative 2, so negative 6 volt. So output is going to be centered around negative 6 volt. And now we're going to calculate the peak to peak value of the AC component. So first we're going to move this square wave about x-axis. So we're going to move this square wave about x-axis. And then the peak value is going to be 1, and then it's going to be negative 1. And then you're going to calculate the area under curve, 0.5. So it's going to be 0.5 milli. 1 times 0.5. It's going to be 0.5 milli. So 0.5 milli times gain of the true integrator. You're going to get, let's see, where did I calculate it? It's going to be 1 volt peak to peak. Total 1 volt peak to peak. So the output is going to be centered at -6. 1 volt peak to peak, that means it's going to go 0.5 volt above -6 and 0.5 volt below -6. So from -5.5 to -6.5. So this is how you can determine the output of an AC integrator. In the next video, we're going to discuss differentiator and the low frequency differentiator.